Okay, good morning, good afternoon, or good evening to everyone, and thank you for joining us today for this webinar about control and automation for radiation processing. My name is Martin Comben. I'm from the International Irradiation Association, and I'll be hosting the webinar today. You may have been expecting to see my colleague Thomas Crock. Unfortunately, he wasn't able to join us, so I'll be stepping in for him today. Just before we start, a few words about the International Radiation Association. We're an association that supports and promotes the safe and beneficial applications of irradiation. We're technology neutral, so we support and represent gamma, electron beam, and X-ray irradiation. And we're also a not-for-profit, so everything that we do is supported and funded by our membership. So if your organization isn't a member of the IIA, I'd encourage you to look at our website. It's iiaglobal.com. And if you'd like to join, please contact us. If you'd like to be part of the IIA community, demonstrate your commitment to irradiation and receive some of the benefits of membership, then please contact us. I'll give you our website address at the end of this webinar. So today we've got two presentations by members of IIA. We've got Rick Black from Black Controls, and he's going to be talking about irradiator control systems and control system upgrades. And we've got Mike Ingles from Applied Manufacturing Technologies, or AMT, and he's going to be talking about automation and material handling. So two quite different but linked topics, and both critical to radiation processing. And it's probably worth saying that this webinar is a result of a discussion that we had at the IIA's Gamma Working Group, and it was and although it was a Gamma Working Group, actually the topics of discussion today apply equally to electron beam and to X-ray technologies, and in fact EO as well, ethylene oxide. Also, just worth mentioning that the Gamma Working Group has been replaced by a Technologies Working Group now, just to reflect the overlapping needs of all the irradiation modalities. The final piece of housekeeping: we're going to keep the questions until the end of the webinar. So you'll see a Q&A tab at the top of the screen. If you could put your questions into the Q&A tab, and then we'll get get to them at the end of the webinar after the presentations. Okay, so with that, I'm going to introduce our first speaker, or our first presenter, who's Rick Black. He's owner of Black Controls Company Incorporated, based outside Toronto in Canada. He leads the company with a hands-on approach. He's focused on practical solutions and long-term client relationships, and he's committed to building reliable systems and a strong collaborative team. Today he's going to highlight how irradiation facilities rely on robust, well-designed control systems to ensure safe, efficient, and repeatable operation. He's going to explore the critical role of control systems, provide an overview of the key components that make up the control system architecture, and highlight some of the key considerations when upgrading an existing system. So with that, Rick, I hope the introduction was right. I'll hand over to you. Thank you.
Okay, great. Yeah, thank you, Martin, for the introduction. Good morning, everyone, and thanks for joining today. As Martin said, my name is Rick Black, and today I'll be talking about controls and automation for irradiation systems, with a focus on how modern control system design improves safety, reliability, and overall system performance. So yes, I'm the owner of Black Controls. We're based in Ontario, Canada, just north of Toronto. We specialize in designing and integrating industrial automation systems in various industries, including irradiation facilities, where safety, validation, and reliability are critical. I'll keep this presentation high level today and focused on key concepts rather than deep technical details. In the next few minutes, I'll touch on the role of control systems in irradiation facilities, how those systems are structured, key components you'll typically come across, how safety, validation, and deployment fit together, and finally, some considerations when upgrading legacy systems. So in irradiation facilities, control and automation systems do much more than move product. They coordinate machine and process behavior, enforce interlocks and radiation protection logic, and provide real-time visibility into system status. Just as importantly, they capture data for traceability, compliance, and troubleshooting, which is essential in regulated environments. When designed properly, these systems enable efficient, repeatable, end-to-end operation while ensuring safety remains the top priority. At the bottom of the screen there, I've included some common acronyms that you may have heard before in various discussions revolving around automation or controls. Most modern irradiation systems follow a layered controlled architecture. Overseeing the whole system at the top, you'll have a SCADA or HMI layer, which provides operator interaction, batch scheduling, alarming, data history, things like that. Below that, you'll have a PLC and safety layer, which executes cyclical machine logic and enforces safety interlocks, things like e-stops, door interlocks, radiation monitoring devices. And continuing the trend, at the lowest layer is the physical layer, which includes things like conveyors, sensors, motors, safety devices, and field instrumentation. All these systems they all work together, and they all need to support each other in order to produce a reliable, scalable, and highly maintainable system. This slide shows a representation of it's an example of some common components that you'll find in automation systems. You'll typically see material handling equipment, conveyors, robotics, barcode readers, and vision systems for product identification, safety devices like light curtains and e-stops, and control hardware such as PLCs, drives, and HMIs. The key takeaway here is integration. All these elements must work together as one coordinated system. In automation environments, safety is designed in from the very beginning. Formal risk assessments are used to identify hazards, analyze risk, and define mitigation strategies using engineering controls, safety devices, and interlocks. Once implemented, systems are validated to ensure they operate as intended. This typically includes installation qualification, operational qualification, and performance qualification. This process ensures not only the system works, but that it works safely and consistently and meets regulatory expectations. Simulation is an important tool that's used during system design. It allows control logic, material flow, and safety interactions to be validated before equipment is built or installed. This can help reduce commissioning time, uncover issues early, and minimize surprises during startup. So this video that's playing is an example of a robotic handling cell. Many irradiation facilities today are operating legacy control systems. Common drivers for upgrades include hardware obsolescence, changing safety standards, spare parts availability, and cybersecurity concerns. Upgrades don't always mean full system replacement. In many cases, controls can be modernized while reusing suitable or existing mechanical equipment. A key goal is to minimize downtime, including reducing things which has a big impact on cobalt decay. So that's a big consideration when you're planning an upgrade. So to summarize, control and automation systems are critical to safe and reliable irradiation processing. Layered architectures improve safety, reliability, and scalability. Proper documentation and validation are essential for compliance. And modernizing legacy systems reduces risk while improving long-term support. These principles form the foundation of safe, scalable, and compliant irradiation control systems. That wraps up the end of my presentation today. So I hope this presentation provided you a useful high-level perspective on how automation and control systems support modern irradiation operations.
Thank you, Rick, for that nice summary, and yeah, good to hear about the work that Black Controls is doing. before we move on to Mike's presentation, I just had a question about, you mentioned legacy control systems, so older systems that really need upgrading for, I guess, continuity purposes. I just wonder, what's the biggest challenge um, when you're planning these upgrades of legacy systems?
Usually it's downtime is usually the biggest concern. So when the upgrade's actually happening, the system is down. So you're not processing product. In a gamma facility, cobalt's decaying and that is expensive. Um, so sometimes what we'll try and do is, or we do a very thorough planning process for the installation, so we can limit that downtime, identify all the risks that we may encounter, make sure we have countermeasures in place, make sure we've got a team. Sometimes we have to work, multiple shifts in a day, just to try and condense that amount of time that the system is down. Things can also be approached in phases. So, reusing some equipment where possible, upgrading controls or safety pieces strategically can help with that as well. So that in these types of facilities, those are, I would say, is one of the main things that we would work through.
I'm sure you're always under pressure to reduce downtime to the minimum. Okay, thank you, Rick. Appreciate your presentation. Just a reminder, please, if you have any questions, put them into the Q&A tab, and we'll get to them towards the end of the webinar after our second presentation. Our second speaker is Mike Ingles of Applied Manufacturing Technologies, based in Lake Orion, just north of Detroit in Michigan. And Mike's going to run through the important considerations when planning automation for material handling at irradiation facilities. Mike's business development manager at AMT, but Mike, I remember last time we spoke, you were just about to go on site and climb under some conveyor system with some welding equipment. So I guess you're an engineer at heart, Mike. Over to you, and we look forward to your presentation.
Thank you, Martin. Yes, while I'm getting all this ready to go here with my presentation, I'm not the most smooth, again, here, we looking at my emails. I'm not the most smooth about presenting, you guys, but I have been I put my first robot in the ground in 1985. I'm sorry, it switched screens on me. I put my first robot in 1985. I cut my teeth in automotive. I worked for 12 years for Fennec, ABB, and GM back in the day. I've been with AMT for 22 years, and for 10 of that 22 years, I was an automation consultant. So what we did is my team and I went from plant to plant to study if you should automate, and if you should automate, should you automate a little or a lot, or what levels of automation. So thanks for listening to me today. Rick did a great job of explaining the controls and automation. I'm going to add to some of the things that he said. So the biggest thing for automation, if you're considering automation, is I'd like to go over these couple highlights here. Some of the sterilization experiences that I've done. Upfront data collection is a big thing. Building the business case, the process specific details, manpower, and then just a couple basic things about controls. Again, Rick did a great job with the controls, so I won't be able to get into that level of detail that he did. The engineering team and a company like Rick and AMT would work together for all those details. Just a brief history, just so you understand where you know that we're coming from. We have done the AMT team, we've done work with E-beam systems from the whole business case development, going, collecting the data, analyzing the business. Was there a business case? Was there not? That whole execution plan. So we have a pretty standard method that we use for E-beam automation. It's trying to make sure that we're not starving or blocking the E-beam is basically what it is. And then the buffer conveyor, the conveyor is going into the tomb. A lot of the E-beams have a fixed conveyor. So the business case would be on trying to be able to accumulate products. So if there's an issue outside of the tomb, outside of the source room, we would never stop or block the U under beam conveyor. We've done work with gamma solutions. We have equipment that we're working on for the mechanical failures inside the actual source room itself. The head count reduction, we're talking about automation for depalletization and repalletization, so that we can control the flow of the product into and out of the going into the gamma facility itself. We do have a couple ethylene oxide chamber solutions that we're working on. We have not executed those yet, but we are working on those with our customer to solve those. And then one of the things we're also under engineering consideration is the AMRs moving autonomous mobile robots moving product pallets from shipping to the gamma or the E-beam or the X-ray, and from those same items out to the warehouse area. So basically from the truck to the sterilization process, and then from the sterilization back to the truck. The big thing when you're trying to do automation is upfront data. I've written a lot of business cases in the last 40 years, and it's a bad data in, bad analysis, good data in, good analysis. So one of the things we'd recommend, if you're going to really consider automation and spending the amount of money that you would do and try to prove the business case, whether you have increased productivity or headcount reduction, would be collection of data. A lot of plants will record data, a lot of plants record downtime, but the operator doesn't want to get in trouble. The operator just puts down some code, or he puts down some reason why the system was down. So we typically ask for 12 months worth of data. So the sooner that you start collecting good data in terms of the downtime, what were the reasons for the downtime? Why was the E-beam starved or blocked? Why was the gamma material having to put back down into the pool? And those recoveries, because those are key items for the business case itself. For the business cases that I've written, most of it really is not a headcount reduction because of the amount of money that can be made during the sterilization process. We typically have increased productivity is more of a bigger thing for the ROI than actual headcount reduction itself. But one of the notes here is when you're talking about headcount reduction, we will typically have to add in skilled trades to maintain the systems, maintain the robots, maintain the automation. So again, that is another reason why the headcount reduction is not typically a big part of the business case. What we try to do with automation too is we also try to have this is not just a sterilization, this is the whole world. When we are trying to do automation, we try not to do everything with automation. If you try to automate everything, it's very expensive. If we follow the 80-20 rule, where you would typically try to do most of the work most of the time with automation, but you have some manual backup spur or some manual lane. So, for example, for the gamma systems or the E-beam systems, we would try to do drums manually, or maybe sometimes plastic containers. We can do bags automatically, but there's a tool change sometimes necessary when you run a different product. So there's a cycle time penalty for things like that. The previous business cases that I've written that have been able to justify spending tens and $20 million respectively per system, we were right around the 75 to 79% of the production was done automatically, and the rest of the product was run through the manual lanes. A big thing for automation also is that as much as you want to get good data up front, we want to define the system. Rick had in his notes about the factory acceptance testing and site acceptance testing. Defining these things up front is very important, because for automation, I'm going to typically set up an entire system in my facility, and I'm going to run the whole thing, and I'm going to need enough data to run it for hours and hours, enough product to run it for hours and hours. So typically, and I've done this myself, like Martin said, I've done welding, I've done all these things. We would buy 25,000 pounds of rice, and we would fill up rice and put it in boxes and run boxes and rice through the system. But we try to run the product that's like what would be running in the facility, so that you have a good example. Before it leaves our place, we would want it to make sure that it's going to run a good sampling of all the product. And then again, the site acceptance, again, at your facility, same thing. Before we actually turn it on, we want to make sure that it actually works really well. Another thing to consider up front is the production support and system training is a big thing, because even though the E-beam is one of the most exciting things I've ever seen in terms of the engineering technology, it's still manually loaded and unloaded in a lot of facilities. The boxes and product are. So even though the plant is really good at the high tech stuff, they're not used to automation. So training up the operators, training up the individuals that will be running the system, that's a big thing. So we do that training up front. Another reason why we run the whole system at our facility is so that we can train those people in our building with their system they will run before it ever leaves our building. We just want to roll those costs into the business case. Process details. I'd like to show you just a real quick video, give you an idea of what we're doing here. So this is just a standard cell, but what if we're going to palletize, repalletize, or depalletize, the whole thing is from a pallet to singulation through the E-beam, or to singulate to get into the totes for the gamma systems. So this is just a standard system that we have, but we're taking a lot of boxes on a single pallet with a large robot, handing it to 3 tables. Then the smaller robots are taking individual packages and singulating them. This is a typical E-beam example for, again, sorry about fumbling around here on the screens. So the biggest thing in terms of automation considerations is the actual product itself, right? That is a video example of picking up a flat layer and handing it to 3 robots and singulating the pieces to go through the E-beam. Same thing in terms of the if we're doing gamma, we're trying to get these. Typically with the gamma systems, you'll have humans still load or unload the totes, and all the automation really be doing would be the repalletization after the gamma. We have come up with examples of methodologies for robots loading and unloading totes, but we have not done that. We have not executed that at a facility yet. But the big thing is for the different types of configurations, if it's a flat layer coming off from your customer, it's easy for the robot to pick up. If it's not a flat layer, or we have different SKUs, the robot can still do that, but there's a cycle time reduction and there's a complexity that gets added to it. So just more, it's a different vision system. Buffer sizes allow for the change in surgeon. So if we are working with automation, it takes a robot longer to pick up 52 boxes off one layer, because it will pick up a whole layer, but then we have to singulate the 52 boxes. If it's a big product, then we're picking them up and it goes, the robots can go faster because the articulation is the same, whether it's a small box or a big box. So some of the things to consider is the size of the product, the way that you run your production. We have our different production runs. I know it's standard in terms of the gamma penetrations and the intensity of the beam, the UBCs under beam conveyor speeds, things like that. For the production variations, we want to make sure that the variations with the actual product don't have big swings either. Another thing is that if I have a barcode from a customer, a lot of it, our customers are driving what we're doing. So if I have a barcode on one side and I'm trying to orientate that, there's actually 6 sides to a cube. So it takes longer for the robot to orient it 6 times or multiple times. So it takes longer to run a product if we can't add a barcode. So we want to add our own barcode sometimes to simplify the automation, but a lot of the customers won't allow that. Another thing is the actual product itself. If there's a 1/4 inch change in product, then I have 12 layers of palletizing. By the time we get to the top, there's 3-inch difference in what the stack height can be. So it changes the vision, changes the details associated with that. So one of the things we want to consider is the product itself when we're looking at all the detail up front for the beginning of the automation. So again, things to consider: layer integrity and pallet integrity are things that add complexity to the system, but they can be done. Changes in height. We do run spiral conveyors, so we have different automations. There's elevators you can use, but typically, if we run higher than a 7-degree incline to get for changes in height in the building, then if we have a box that's square and we have a center of mass that's above center, that we have had boxes tumble down in the manual load stations. So it's things to consider, all the things to consider in terms of the actual automation itself. Our standard system is typically around 50-pound boxes. Anything above 50 or smaller than 2 would typically go to the manual lines, if that makes sense, the way I'm describing that. So it's again, understanding the process details before you do the automation is something to consider. We've looked at as many as 1,500 SKUs. We mark those, we put those in families, we sort those so that we look at what the product can and cannot do, what the automation can and cannot do. One of the recommendations for the automation considerations is dedicated project managers on both sides. Your customer and you and the automation team, or you and the automation team typically have to have dedicated project managers for that entire process. Things run smoother, things run better if we have one person to focus on that the entire time. The data entry product for the product is something that Rick was getting into a little bit. He has all the 3 layers. We've found that we put automation in, and it makes it easy for moving the product around, but sometimes it adds levels of product data entry in different parts. So when Rick's talking about the different layers, we want to make sure that we understand Rick's type of work up front and who is going to be handling the process, the data entry, things like that. Again, back to the training of the operators prior to the system arriving is a big thing. The amount of product I already touched on that needs to come to the factory's integrator. We've been able to do multiple E-beam sites, and some of those sites have greenfield areas. So we've been able to actually install the robots and have them actually run fully and run off and accepted. And all we had to do was just a weekend tie-in. So like Rick was talking about the shutdown on one of our E-beam system, the shutdown was only over a weekend, and we tied the whole thing in. And on Thursday, it's running with the old system. On Monday, it's running with the new system. One of the other systems that we did, it took us several weeks of lack of production because we had to literally rip out some of the old equipment and put new equipment in that same location. So again, the layout is a big function when you're considering automation. It's how are you going to put it in there and what you're going to do. Basic controls, things that Rick talked about, the plant IT, the system IT, operator training. Again, Rick talked about a lot of these things down at the bottom, so I won't get into those, but I'm sorry, but working on the control system is something that you have to get into greater detail. I'm floundering a little bit here, so I think it's a good time for me to step out here. But if I go back to the beginning, upfront collection of data, looking at the business case itself as typically increased productivity, not headcount reduction, and then all the process details, taking a look at all the process details and considering all those things long before you get those in. So writing those into the specification, system specification is a big thing. Martin,
Mike,
I'm going to ask you to jump in. For some reason,
yeah,
I'm
no,
having
that
a
was
little bit of a
great.
brain
And
freeze here. No, that's all right.
it was really thorough, and we appreciate all of the detail that you went into. It's clearly, I have a question for you, Mike. So you're not off the hook just yet. What you talked about is highly complex, and the equipment that you supply, it performs multiple different functions. And those functions will be different from user to user or from site to site. And the question really, I guess, is how do you get that specification from your from the operator of the irradiator site?
So, again, some of the customers that we work with are highly educated in how to write specs and what to do. So they'll have their own specifications that they will write. It'll typically be a 20 or 30-page document that describes each process step, and it breaks down each process step and how we want the data to flow for that process, how we want the material to flow for that process, what we'd like to do. Other customers that we've worked with didn't have a deep engineering team to write their own specifications. So what we've done is we've helped them author some of those specifications with some of the considerations for automation that we've done. So we will interact with their team, we'll work with their team to co-author that specification. And the user specification really is to define what the goal of the system is, what the input values are for that system in terms of data or product or speeds or cycle times, and then the output of how fast the system will work, how it will work, how things will move around. So again, customers can write their own specifications around all the processes, or we can help author those, co-author those specifications. But most of it, Martin, is about process and understanding up front the detail.
Right.
Thank you for that question.
Okay. So it's so it's a collaborative effort. I guess the trick is to get it as accurate as possible, as early as possible, to avoid having to make changes as the system develops.
So again, I'm not a polished presenter. I was not as smooth as Rick, but I did start with a data in, data out, right? Good data, good specifications, good information on the downtime, the reason for the business case. Those things are very important to make the engineering side of it go smoothly.
Thank you, Mike. Yeah, that's very clear. Okay, so we're going to move on to the Q&A phase. We got a few questions. If you have any questions, then please put them into the Q&A tab. I have a question for Rick. Rick, maybe you could put your camera on.
Yeah, there we go.
Thank you. Thank you. So the question is, what part of the control system architecture is most critical for maintaining safety and regulatory compliance within an irradiation facility?
I think for the safety side, I guess the most critical thing, like when it's actually operational, would be the safety PLC. That's the safety PLC is making real-time decisions. It's monitoring all the interlocks and switching things off. But having said that, like we're talking about looking at the big picture here, a strong safety system starts in the beginning with a comprehensive risk assessment and robust system design, deployment, and validation. So once it's all set up, I mean, the safety PLC is what's going to maintain that safety while you're running. But it's only going to be as good as the overall safety design, which starts early on in the process and gets carried through to make sure it works. And then on the regulatory side, like a well-implemented SCADA system will complement that. It's going to be able to track a lot of data that's necessary as products treated about the batches that are run. So a well-designed SCADA system, again, if those details are hashed out in the beginning, they can be implemented into it. So that way it's, trying to take off some of that data recording and report generation and things like that are necessary.
Great. Thanks, Rick. We got a question about the key challenges when upgrading control and automation systems in older irradiators. And I think, Rick, you answered it. The key challenge being downtime and reducing that downtime. Mike, does your organization, AMT, do you install only new systems in new facilities, or is much of your work upgrading existing systems and modernizing existing systems? And if so, what do you see as the key challenges when you're upgrading an old system?
So if anybody's been in a gamma actual source room and seen the glow in the dark pool, right? You see how it erodes the steel. You see how it wears down all the equipment in the room. And because of the thickness of the walls and because the limited penetrations into and out of the interim and out of the top of the ceiling, right? We have actually worked with a vendor of ours, and we're designing a gamma room installation where it's kitted in pieces, and we'll be covering up the pool, of course, initially with the new equipment, a new cover, and we'll be taking out all of the old steel. We'll be building something that's an internal structure inside the existing room, and then we'll be kitting all that. And all the beauty of that is we'll have run all that at our facility because it's kitted, because it's a complete new structure instead of embedding it into the cement of the source room. We'll have the ability to run that entire system. Unfortunately, our customer has to buy 87 new totes, but we'll be running all the totes and that entire system in its entirety in our facility and running it off. So when it gets to the plant, even though we have to get all that old equipment out and put the new equipment in, we will have run it and built a new superstructure inside the source room instead of penetrating the cement. So I hope does that answer your question, Martin?
It does, and I guess it reduces downtime as well, and it makes maintenance easier. You know, if you do need to access that piece of cable or that bit of equipment, it's not embedded in the concrete. You can access it easily, right?
So some of the upgrades are, yes, is the older systems, the older Nordion system, I do believe is the one that we're working with, is a 30-year-old system. And the cylinders and the pushers for the top row of the totes is up near the ceiling. And the maintenance people have to get on ladders over the pool and do all that work. So we're gonna put some of those things closer down, better access for the maintenance team. So it's just, those are all interactions with the plant, all through the design of the system and all through before we even did the business case, we got into that level of detail to write the business case to make it easier to work on. With a more modern system, it should be easier to work with. That's all, right?
Perfect. Thank you. Rick, question.
Or just I have one point on that too,
Sure.
just about the older systems. Another thing too, yeah, when you're actually doing the deployment, the downtime is, you want to plan to try and limit that. But yeah, because a lot of these systems are quite old, some of the documentation just to try and find out like how it's currently functioning can be limited, or it can be obsolete because, maybe a system's been running for 20 years and there's been things have broken and they've been replaced. Maybe they don't match the drawings anymore, the way the system was originally designed. Or maybe there's been some, ad hoc upgrades added to make improvements. So, I mean, when you're doing an upgrade, you don't want to take any functionality away. You want to improve on what's there, but understanding the nuances of how the system is set up, for a particular bunker and a particular site, can take a little bit of time to get those details. So it's important to upfront, spend time with the customer, understand how their system currently functions, and then look to improve that. And sometimes that can be challenging just because of the nature of, how old some of the systems are.
Got it. Thanks, Rick. We just had a question, a great question. I think it's probably for Mike, but maybe Rick, you've got some comments. It's, what are the biggest failure modes that you've seen in automated conveyor systems, and how are they mitigated in real time to prevent non-conformance when processing product? So where do you see failures in conveyor systems, in maybe older systems, and what can you do to ensure that there's no non-conformance of the process that's product because your system has failed? Not your system, but the system has failed.
So if we're talking about the actual conveyors in the high risk areas, for E-beam, for example, because again, it's mostly mechanical devices in the gamma room. It's not as much driven conveyors, but it's pushed around with the cylinders. But in the E-beams, we're working with the customer to talk about the physics. Again, we're robot and conveyor dorks, right? I'm not a physicist, right? So we're working with the customer on what products can we use, what lubricants can we use, what are the details of the actual things in terms of the physics that go through that. But in terms of making it more robust, one of the things that we've done, or we are considering doing with our customer and working with the customer, is that we're trying to make it more modular pieces so that if there's something that needs to be worked on or done, I don't have to shut down the whole thing or rip out the whole thing. I only could do sections or smaller portions of it. So understanding the failure points and the things that go bad in that harsh environment and make it those things readily interchangeable, I guess Martin would be an example of what we would do so that there's just in the design consideration, there's maintenance, rapid maintenance procedures that would be designed into the system, if that makes sense the way I'm describing that. So I
Yeah,
don't know
that
if that
makes
answers
sense.
if that answers your question correctly or not.
Yeah, well, I think it answers half the question that came in. Maybe the other half is for Rick, or maybe I'm confusing control systems with product tracking systems here. But Rick,
Yeah, for me, one thing
if
that
there is a failure and the irradiator stops, how do you ensure that that there isn't a non-conformance because because the product has stopped in the cell part way or something like that?
one thing that can be done to try and keep a process running, if you build some redundancy into it, for example, if you have sensors that are detecting product, if you have multiple sensors doing the same thing in parallel, what can happen, what that can allow happen is a sensor could go bad during a run. Let's say you've got a bunch of product loaded up, you're in the middle of a run. One sensor could fail, which isn't uncommon in, the radiation environment. It could be due to a cable, it could be due to a sensor. There's lots of reasons why things could go wrong. But if you've got that redundancy, then the system could flag that, hey, this sensor's failed, but because there's another one there still detecting product, it could keep running and finish the batch. And then it could be changed later, like as opposed to just like, we don't know where product is anymore at this juncture where that sensor failed and we can't run anymore because you're not able to detect it. So as a way to, I guess, mitigate or not have a scenario where you need to like just shut down in the middle of a batch for a single point of failure, you can build some redundancy in those areas where failures are common. So I think maybe that touches on the question.
Yeah, it does, and I guess over time, you become familiar about where the weaknesses are in any system, and you can manage accordingly. Rick, I have another question for you, and it's about the formal safety risk assessments and the validation process. And perhaps you could just highlight why that's so important in irradiation control systems.
Yeah, it's definitely important in irradiation because the risk is so severe with radiation, and it's important in just in automation in general. But the reason you want to, hash out those details in the beginning is because it's difficult to change it after the fact. I mean, if you design this whole system, and you haven't identified all the hazards adequately in the beginning, then those hazards aren't going to be mitigated through your design process. So. Yeah, ensuring you do that risk assessment in the beginning and carrying it through into your, FAT, SAT, through your IQ, OQ documentation, it proves that, by following that through, it proves that the system functions as you intended, and it works consistently, and it basically is in compliance with all the regulatory requirements. I mean, we usually look at safety a little bit higher because it's safety, around humans and the environment. But it applies to the whole process as well. If the more you can hash out and better define it in the beginning, and Mike's talked about this a lot as well with the URS, the more you can define all those key details, the safety system is a part of it, then you can efficiently design the system to cover them, and then validate that it does do that once it's all put together.
Great. Thanks, Rick. Just one other question. Have either of you had any experience in working with low or medium energy e-beams? And if so, are there any particular considerations for lower power machines? I suspect the control is the same, but I've just wondered if there are any other considerations.
Yeah,
I yeah.
or go ahead, Mike.
No. I was just say I don't have any experience with a low uh with that scenario, so I would have to defer to Rick if he has any experience with that.
Like you said, I mean, the overall, um, like process is usually similar, like for sterilizing a product, or treating a product with radiation. Like if you've got lower dose, then the shielding probably doesn't have to be as substantial. So maybe the way that you deploy the system, the way you wire things, the conveyor design, maybe doesn't need to be as robust in certain areas. So yeah, I think it definitely has an impact, the level of radiation that the system's dealing with. Do you have a huge bunker, or maybe you've got something smaller, or like a self-shielded machine? So in general, there's still going to be sterilizing or treating something, but the methods you use to actually complete the work, the wiring, the mechanical components, etc., they can vary quite substantially depending on the radiation levels. Size of product is a big thing too, right? If you want to treat big product, or if you want to treat small product, that has a consideration as well, like for conveyor design, robot design, things like that. If you got to pick something up heavier than something smaller, a lot of stuff all has to be considered. So, yeah, I think the radiation level is something that's important to consider too, and it does definitely impact the system overall.
Perfect. Thanks, Rick. And I think just one final question, and we talked a lot about safety, and this is for you, Rick. We talked a lot about safety. We haven't spoken about security. So in terms of security for gamma radiators, and I know safety and security is often used in the same sentence, and it's often confused, but by security, I'm referring to, protecting particularly cobalt sources, but also general business and operation from people who want to do malicious harm. So, like, for example, cybersecurity is a pandemic of cybersecurity here in the UK, and I don't know what it's like where you are, but I guess cybersecurity and other physical security systems is also a key consideration.
Mm-hmm. Yeah, like facility, though that normally we don't normally get involved in that. Like the operators of the facilities take care of I guess security like at the facility level. In terms of cybersecurity, it's definitely a consideration, because these systems get installed all over the world. Being able to access them remotely through the internet has a lot of advantages in terms of troubleshooting and supporting customers while they're running. So when making those connections, putting them on the internet, they're obviously exposing the system to potentially a cybersecurity incident, right? So there's different ways of connecting to equipment. Sometimes you can buy a module that you would install in, say, a control panel that would allow you a secure connection to the PLC, and the customer may not know about that, or it may not go through their network infrastructure. Another method can be a customer can set up like a VPN connection using their internet connection. So a lot of times the end customer will want, because it's their machine and they're the ones at risk from this cybersecurity attack, and it's usually they want to have that connection as part of their overall IT. So usually they'll give us a VPN connection that they'll manage, and we'll use that to connect. But in cases where customers don't have that already set up, there's alternatives too. So like anything, there's lots of ways to do it, but it definitely is a consideration, because, like you said, there is a lot of cybersecurity incidents happening, and there is a risk there. So, with convenience and troubleshooting, all those benefits, which is the reason why you would do that, you do have to think about and plan for the negative implications that could come out of that, and a cyber attack is definitely one of those.
It certainly is today.
Mm-hmm.
Good. Well, we've run out of questions. I think you've been very clear with both of your presentations. So I think we'll draw this to a close. Thank you to both of our speakers, Rick Black from Black Controls and Mike Ingles from AMT. We really appreciate your contributions today. Rick and Mike's details are going to come up on the screen at the end of the webinar, along with my details. If you have any more questions, then you can direct them to me, and I'll forward them onto one of the two speakers. Thank you to everybody who's joined us today. Please keep an eye on the IIA website and our LinkedIn, and sign up for our IIA newsletters just to keep updated about future webinars, about general industry news, and also about the 21st International Meeting on Radiation Processing that's happening in April next year. With that, again, thank you, Mike. Thank you, Rick. That was excellent.
Thank you, everybody, for listening.
Let's keep in
Yes.
touch, and we'll speak soon. Thank you very much, and goodbye.
Thanks, Mike. Thank you,
Thank you,
everybody.
everybody.
Thank you.